Yes, in this video, we will see the post-processing part in STAAD Pro. Okay, so for which we will be modeling a simply supported beam of span 6 meter. So we will be considering dead load 10 kilonewton per meter and live load 15 kilonewton per meter. So in addition to dead load and live load, there will be a self weight. The beam which is modeled is ISMB 600. Okay, first you open STAAD Pro. So length of the beam is 6 meter. You create a node at 0, 0, 0. So next node will be at a distance of 6 meter, 6, 0, 0. Okay, so this is your first node 0, 0, 0, and this is your second node which is at a distance of 6, 0, 0. So again we will have a beam. So go to add beam. Okay, the beam is simply supported beam. So you go to properties, legacy. The section is ISMB 600. So we will look for ISMB 600. Yes, it is your ISMB 600. You click on this add button, close. You select this beam. You go to assign. Yes. So this is your ISMB 600. So you go to beam tools. You can see the 3D render view. So this is your I section. So this is your ISMB 600 section. Okay. So supports. You go to create pinned. So to resemble the simply supported, you go to add. See here, supports are assigned. Next coming to loading. So you go to reference load definitions. You click on add. So you click dead load. So otherwise we can have self weight first case. So next will be dead load. You click on add. Next live load. So you click on add, close. So we created 3 load cases. that is self weight, dead load, live load. So first we will assign self weight. So go to add. So self weight y direction factor -1. You click on add, close. You select this beam. You select this self weight, assign. Okay. Next, dead load. So dead load 10 kilonewton per meter. It is UDL. So go to member load. So -10. You click on add, close. You select this beam. You select this load, assign to selected beam. See here. So this is your dead load 10 kilonewton per meter. Next, in live load, you click add member load. So live load it is 15. You click on add, close. Oh, you have to change the sign. So it is -15. -15 modify, close. See here. So self weight -10 -15. Next you go to analysis. Analysis command, all, add, close. So we will add a combination. So we will add a one combination, that is we will add a one combination, load combination 1.5 dead load plus 1.5 live load. Dead load means it is including your self weight. Okay. So you go to load case details, add, define load combination. So to create load combination, in case of load case details, again you need to create cases, load cases. That is, first one is self weight, add, close. So second case is dead load, add, close. Next is third case is live load. So in case of self weight, you go to add, repeat load, reference load. So self weight with factor 1, add, close. Next, in case of dead load, reference load, dead load, add, close. Live load, add. So you go to repeat load, so close, you delete this. So it is a dead load. So you bring dead load here. Next, in case of live load, add repeat load, reference load, live load, add. Okay. So R1, R2, R3. So load case details, add, define load combination. So it is 401. Load combination is 1.5 DL plus 1.5 live load. So self weight, it is factor 1.5, dead load with factor 1.5, live load with factor 1.5. So you add, close. So you go to run analysis. So you click on this, go to post processing mode, or you can click this stay in modeling mode. So stay in modeling mode. So in STAAD, you have two axis system. So this will be your global axis system. So to view the local axis system for member, this member, you click shift O. See here. So this is the local axis system. Okay. If you zoom in, so you have three axes, three directions. So first color is blue, red, green. So blue is local X, red is local Y, and green is local Z. Okay. So if you take any software, ETABS or STAAD Pro, analysis outputs are given to you with respect to local axis, not to the global axis system. So local axis X is along the length of member. So if you see this blue color axis, it is this blue color axis is along the length of the member. So blue is along the length of member. So next, your red axis. So I will try to use same color. So blue, which is X, red, which is Y, and green is Z. Okay. So your y-axis is along the depth of member, and z-axis is along width of member, along the width of member. So you can have the 3D eye section. So if it is your eye section, see here. So this blue color axis is along length, and this red color axis, it is along depth, and this green color axis, which is along the width. So blue refers to local axis x, it is along length of member. Red is local axis y, along depth of member. Green is local z, along width of member. Okay, so this is the local axis system in STAAD Pro. So what are the analysis outputs we can have? So analysis outputs are moments and forces. Okay, and we will be having the deflections also. So majorly we concentrate on moments and forces. So in moments we have mx, my and mz. So for forces, fx, fy and fz. So in STAAD Pro, forces are represented in along sense. So forces are represented in along sense, whereas moments are represented in about sense. Okay. So you go to view, isometric view. You go to beam tools. You select this 3D rendering. See here, x-axis will be along length, y will be along depth, and z will be along width. Okay. So in STAAD, forces are represented in along sense. So if I say fx, so whenever I say fx means it is force. Okay. So force along x direction. So it may be either in this direction or in this direction. See, if this is your local x, then fx means it is along this direction. So this type of force we call it as axial forces. So either it may be tension or compression. Okay, so whenever I say Fy means, so this is Fx. Whenever I say Fy means force along y direction. So which is your y direction? So this direction. So this is called as Fy, or in opposite direction. So these two are called as Fy. Okay. Whenever I say Fz, whenever I say Fz means force along z direction. See, this is your z direction. So this is parallel to z, and it may be in opposite also. So this is Fz. See here, you should clearly know the difference between Fx, Fy, Fz. So Fx is axial force, whereas Fy and Fz are shear forces. Shear forces. So this axial force is perpendicular to cross section, whereas this shear force Fy and Fz are parallel to cross section. Okay, so Fy, so out of this Fy and Fz, so Fy we call it as major shear. And Fz we call it as minor shear. Okay, so whenever we have gravity loads only, so in this case we have only Fy, we will get only Fy, so no Fz. So sometimes your Fy we call it as major shear, because it is acting along major dimension of steel section. So major direction is depth. Okay, so this is acting along major dimension of steel section. So whereas Fz we call it as minor shear, because Fz was acting smaller dimension of beam cross section. Okay, so this is about forces. Next, while coming to moments, so bending will be represented in about sense, or we will be rely on right hand thumb rule. Okay, so this is your axis Z, so this is your y axis. If it is your x axis along length, so whenever I say mx, which means moment about x, so you hold this axis, you use a right hand thumb rule, you hold this axis by your thumb, right hand, you hold this x-axis in your right hand. So your thumb will give the direction of force. Your thumb will represent the direction of force, whereas your fist, it will represent the direction of movement. Okay, so you hold this axis by using right hand, right hand. So this is your thumb. So this thumb will represents the direction of force, which is Fx. So this fist will represent moment mx. So forces are along the direction, whereas moments are about. So here mx we call it as, so which type of bending it is? So it is mx is your torsion. Mx is your torsion. So next my, again same rule is applicable. You hold this, in a right hand, right hand. This thumb will represent Fy. This fist will represent My. So because of this My, so My will try to bend this beam in this direction. Okay, so your beam will try to bend in this direction. Okay, in this direction. So My is minor bending. So we call My as minor bending. So in case of MZ, so similarly you hold this Z axis in right hand, like this. So this thumb will represent Fz. This fist will represent MZ. So this will represent MZ. So MZ will try to rotate this beam like this. So because of which your beam will bend like this. Your beam will bend like this. So MZ is major bending. MZ is major bending. Okay, so this is about moments. I completed this topic in ETABS also. While discussing the ETABS software, I discussed this concept. You just refer to those videos. So in case of analysis outputs, we have Fx, Fy, Fz. So these are forces. So forces are looked along direction, whereas Mx, My and Mz are moments. These are looked about the direction. Okay, so Fx is axial force. Fy is minor bending. Sorry. This is Fy, which means shear, or we call it as major shear. So Fz, it is also shear. So this is minor shear. So mx is your torsion. My is minor bending. Next, mz, major bending. So we have 6 analysis outputs. In addition to that, there will maybe deflection also, but these 6 are with respect to local axis system, whereas deflection is with respect to global axis system. Okay, so once you complete the modeling, so you go to analysis, run analysis. So now you click this go to post processing mode. You click on this, done. Okay, all the load cases are selected. You click on apply. Okay. Okay, see here. If you see here, you have Fx, Fy, Fz, Mx, My, Mz. Okay, so if you click this Fx, axial force in x-axis, Fy, shear force in y-axis, Fz, shear force in z-axis, Mx, torsion force. Next, My, bending moment about y, Mz, bending moment about z-axis. Okay, so there we will see the nomenclatures. I hope you remember this span is 6 meter. Okay, so this is simply supported. So this is ISMB 600, and we loaded this beam with a dead load of 10 kilonewton per meter and live load of 15 kilonewton per meter. Okay. If you want to see the bending moment, so it is simply supported beam. So bending moment will be WL square by 8. So W is, okay, we will take a dead load case. So for dead load, so dead load it is 10 into, so span is 6 square divided by 8. So we will solve this. So 10 into 6 square divided by 8. So it is 45 kilonewton per meter for live load. So WL square by 8. So live load, which is 15 into 6 square divided by 8. So 15 into 6 square divided by 8. So it is 67.5. For live load, bending moment is 67.50 kilonewton meters. So we will check the results. So these are your bending moments. Bending moments. Okay. So we will look for MZ. MZ. So you click this MZ option. Okay. So you go to view. You have the front view. Okay. So this is the bending moment. MZ. For which case it is? This is for live load. So to see the values, you go to annotate, beam results, bending. You click this maximum, midpoint, annotate, close. See here, I have taken the case as live load. So my manual calculation, it is 67.50. My STAAD calculation is also 67.5. The variation will be parabolic. Whenever you have a UDL, the bending moment variation will be parabolic. Okay, so 67. If I change the case here, instead of live load, I will select dead load. So for dead load, so my manual calculation is 45. In STAAD also I am getting the correct answer. Okay, in STAAD also I am getting the correct answer of 45. So this is bending moment. Next, for shear force. For shear force, we will click this Fy. For shear force, we will click this Fy. Okay. So this is simply supported beam, 6 meter span. So it is loaded with live load of 15 kilonewton per meter, and it is loaded with a dead load of 10 kilonewton per meter. So 6 meters. So total load will be, so here, so for this case 15 into 6, so total load 90. So you should get shear force of 45 kilonewton in this case. So in this case 10 into 6, 60. So half of that. So in this case you should get a shear force of 60. So not 60, 30 in this case. So half of 60, it is 30. So shear force 30 kilonewton. So this is your live load case. This is your dead load case. So we will check the shear force results. So you click on this Fy. Okay. Fy. Again you go to annotate, beam results. You go to beam results. Okay. In case of shear, you check this maximum ends, midpoint, and you click this annotate, close. See here. So for dead load, my manual calculation is 30 kilonewton. If you check the STAAD for dead load, so your shear force are 30. Okay, the variation will be linear. Whenever you have a UDL, the variation will be linear, which means straight line. Okay, so now we will change the load case here. So instead of dead load, we will check live load. See here, for live load, my manual calculation was 45 kilonewton. So it is exactly 45 kilonewton. Okay, so this is about bending moment and shear force results. So next we will check deflection. Next we will check deflection. Okay, so we calculate for a simply supported beam with UDL. We calculated deflection by using formula 5W L power 4 divided by 384 EI. Okay, so from steel table, so for this ISMB 600, so IX will be 9.15 into 10 power 4 centimeter power 4 from steel table. You refer to steel table, and your elastic modulus 2 into 10 power 5 Newton per millimeter square. Okay, so here L is constant, E is constant, I is constant. You develop a equation like this: delta equals dash times W. You develop a equation like this, which means you simplify 5 L power 4 divided by 384 EI. 5 L power 4 divided by 384 EI. So here L is 6 meter, 6000 millimeters. Okay, so we will try to simplify this. So 5 into, first you convert this IX to mm power 4. So your IX value will be 9.15 into 10 power 8 mm power 4. So 5 into span is 6000. Power 4. So divided by 384 into 384 into E is 2 into 10 power 5 into I is 9.15 into 10 power 8, which is 0.0922. So which is delta equals 0.0922 times W. Okay. So next we will calculate the deflection. So deflection for dead load. dead load. So equation is 0.0922 W. So your dead load is 0.0922. Dead load it is 10 kilonewton per meter. So 0.0922 multiplied by 10. So which is 0.922. So deflection is for dead load. For dead load case 0.922 millimeters. Similarly for live load. So deflection for live load it is 0.0922 into dead live load is 15. So 0.0922 multiplied by 15, which is 1.383. So deflection for live load it is 1.383 millimeters. Okay. So to check the deflection, you click this deflection button. So deflection. So first case is you select dead load. So you go to annotate beam results. You remove see here. This is the deflection. So in case of annotate, you go to beam results, you select this displacement, you click this maximum result, go to annotate, close. See the answers. So now you are checking the deflection for dead load case. So your STAAD Pro will give deflection of 0.907. So your manual is 0.922. Okay. Next for live load, see here. Your manual calculation is 1.383, whereas the STAAD reflection is 1.360. Almost it resembles your manual calculations. Okay, you can similarly check the deflection for self weight also. You go to self weight, see here, this is the deflection for self weight. And if you have created a combination called 1.5 DL plus 1.5 LL, for the combination also you can check the deflection. See here, for that combination your deflection is 3.565. So this is how you can check the deflection results. To change the scale of this deflected shape, you use control button on keyboard and use mouse scroll button. You can enhance this view. Okay, next we have beam stresses. So beam stress, you go to annotate beam results. See here, this red color is compressive stress. It represents compressive stress. This blue color, it will represent tensile stress. Tensile stress, because your section is I section, ISMB 600. You modeled it like this, I section. Whenever it is loaded with UDL, so this will bend like this. It will bend like this. Okay, this is your neutral axis. So top fibers are subjected to compressive stress, whereas bottom fibers are subjected to tensile stress. Okay, for ISMB 600, from steel table you extract ZX value, so that is 3050 centimeter cube. Okay, you convert this to 3.05 into 10 power 6 cube. Okay, so formula for maximum bending stress. So bending stress sigma equals m divided by z. Okay, so m is your maximum bending moment. WL square divided by 8. Okay, so I will check for any one case. I will check it for dead load. So your dead load is 10 kilonewton per meter. Okay, so for dead load, so W10 into span 6 square, WL square by 8. So moment is 45. So maximum moment is 45. So your load is in kilonewton meter. So 45 kilonewton meters. So which is 45 into 10 power 6 Newton millimeters. Okay, this is the maximum moment. So sigma equals 45 into 10 power 6 divided by, so your Z 3.05 into 10 power 6. So here 10 power 6, 10 power 6 get cancelled. So 45 divided by 3.005. So which will be 14.75. So your bending stress 14.75. 14.75 Newton per millimeter square. For what load case it is? It is for dead load. This is for dead load. So you go to beam stress. Okay. You select this combination dead load. See the results. See the results here. So it is 14.95 Newton per mm square. So for a dead load. Okay. So similarly, you check for live load also. Similarly, you check for live load. So this is one way of checking your analysis outputs in STAAD Pro. So another way is you just double click on this beam. You just double click on this beam. You go to shear bending. You go to shear bending. See here you can view bending Z, bending Y, shear Z. Okay, for various load cases. Similarly, select the different load cases for dead load, live load, 1.5. Okay, so bending Z for dead load it is 45 bending. So shear Y it is 30. Okay, so here you can check bending moment and shear force values. So adjacent to that you can check deflection. So deflection along Y direction. So you can check for various load cases. Okay. Similarly, you created a combination. It will also appear here 1.5 DL plus 1.5 LL. So for this beam, loading was self weight. Another one is dead load. Next live load. So property which is steel ISMB 600. So ISMB 600 for which it will automatically take its properties from steel table. So click on this geometry. See here, your first coordinate node is 0, 0, 0. Your second coordinate is 6, 0, 0, which means length of the beam is 6 meters. Okay. So this is the second way of checking the analysis outputs. So second way is you just simply double click on this beam. Okay. So in case of results, so you click this layouts. You click this layouts. In case of beam results, you click this graphs. See here, the results will appear in the form of graphs. So this is your MZ and FY. At the same time, we can view bending moment also and shear force also. Okay, this is for dead load. So if you select live load, automatically it will change. The results will change. If you want any other graphs, you click here, you go to diagrams. If you want, you need stresses, you select this stress, you click on OK. See here. So this is your stress diagram, combined stress diagram. If you want, you go to right click here, diagrams. You need torsion, you click this. So torsion is 0. Okay, you can bring any number of graphs at a time. You can bring all the graphs here. See, if you want to close this, you just drag here and you click this close button. You can maximize or minimize this. See here, you can maximize or minimize this graphs. So this is the third way of checking the results. Okay, so this is the first part of analysis and interpretation of analysis results in STAAD Pro. Okay, so this is not the end of the session. So tomorrow we will have a discussion on the same.